presentation. I've been looking forward to this visit for a while, and it is, in fact, great to be here, so thank you. This talk is, as Jeff said, going to be about Internet architecture. The first part of the talk will be about network policy, specifically which entities should control network communications and the types of control they should exercise. The second part of the talk will be about mechanism, specifically how to provide that control efficiently, how we actually built it in hardware, and what the uses of the approach are. Now, before getting into the content, though, I want to make two prefacing remarks. The first is that, as you can see on the slide, this has been a highly collaborative project. I began it when I was a postdoc at Stanford under the sponsorship of David Maziere, and we recruited an excellent student, Jad Naous. I'm now working with an excellent student of mine, Arun Sira, as well as two great faculty members, Antonio Nicolosi of Stevens and Scott Schenker of Berkeley. The second prefacing remark is that, as Jeff knows, and maybe some of you know, I'm not operating on a lot of sleep here. It's like about 2 hours or something. So this talk may be on the coherence challenge side of things. For that, could you maybe stop taking pictures? Thanks. Sorry, it's distracting. Sorry. So on the coherence, I may be a little bit coherence challenged, and for that reason, and I'm sorry, I just have a thing about pictures and stuff. If you would be kind enough to interrupt if I'm not being clear, I would be most grateful. I mean, if the interruptions get to be too much, then I'll cut content or defer them to the end or something. But please let me know if things aren't clear. I welcome them, the interruptions. Okay, in moving on to the policy part of this talk, I'd like to observe that over the decades, there have been a lot of appealing proposals concerning different types of network control and regarding different network stakeholders. And the first category of network stakeholder that you might think about, there's a bunch listed on the slide, but the first and most obvious are senders. And there have been proposals to give senders control over the paths that their packets take en route to destinations. And people have observed that it would be good to give senders that control based on, for example, a path's price, its performance, or even a sender's preference for particular providers. Likewise, if there's another category of stakeholder in any network communication, and that's the receiver. And people have observed that receivers have exactly the same interest as senders in the paths that their packets take. The receiver might have its own preferences about which providers carry traffic to it. But receivers have other considerations as well. They might want traffic headed to them to go through, for example, a scrubbing service that's located off-site, for example, to clean network traffic from viruses and so forth. People have proposed allowing receivers to, or that if a receiver doesn't want to hear from a troublesome sender, that troublesome sender's traffic shouldn't even enter the network and consume resources because the receiver never wanted to hear from the sender in the first place. So that's a second category of network stakeholder. And a third category of network stakeholders, providers, of course, which today exercise control over communications, both in terms of the routes that they advertise, which peers they advertise those routes to, and also the downstream paths that they attempt to direct, packets along. And some have observed that while providers are key network stakeholders, they should have even more control to be able to express their business and policy interests and so forth. And there are other categories of stakeholders as well. There are edge providers and middle boxes and people have proposed giving them control over the flows that cross their network as well. So at this point in thinking through all of these stakeholders and all of these different concerns and controls, it's worth asking ourselves, where as a community of researchers, as people who think a lot about networks, people in the IETF, et cetera, where do our sympathies lie? It's worth asking ourselves, and it's probably worth asking yourself, just even as a thought exercise, where do your sympathies lie? And it turns out that your sympathies are probably all over the place if you're representative of the community, because there have been tons of network layer proposals and defenses that have been advanced. And it turns out that each of these generally lodges a different type of control with the different network entity. And to make this point about lodging different controls with different entities in the existing literature, I'm going to depict on the next slide the design space in abstract terms to try to make this point more vivid. So in this abstract depiction, the entity controlling a communication will be the red X. In this case, it's the sender off on the left. I guess that's this side for you. The blue circles will be that aspect of the communication that's under the controlling entity's control. So in source routing, of course, the sender chooses a route toward the receiver. In the NERA proposal put forth a few years ago, senders and receivers can each control a portion of the path that their communication travels over. So what's depicted here is the sender, the red X, controlling the path of a communication into, for example, the network core, and the rest of the path being unconstrained. That's what the black dash means. The receiver has the ability to control communications toward it, to choose the path that packets take from the core toward it, but has nothing to say about how packets got into the core. A third category of proposal concerns network capabilities, and I'm distinguishing between network capabilities and Alex and Bharath Raghavan's work on Platypus, which I'll talk about in literally just a few seconds. In network capabilities, receivers, again the red X, have the ability to say, no, I don't want to hear from that sender, or yes, I do want to hear from that sender. And you can think about that as the receiver not only exercising control over the sender, but also exercising control over the first component of the path that packets take toward it, but having no control or no say over anything other than the sender. And that's what the black dashes are doing there. So in terms of the Platypus proposal done right here, it's loose source routing, so the sender can certainly choose the path that packets take after it. Providers have the ability to associate a communication with a particular principal, often the sender, but not always, build that principal or associate the communication to a principal, which is depicted here as the provider controlling the sender and the receiver, though, of course, the provider inherently can control the prior, or actually can't always control the prior hop, but it inherently, of course, can control the next hop in the communication. And there are other proposals as well, both those depicted on the slide and many others in the literature. I mean, we could draw these boxes and, tic-tac-toe diagrams till the cows come home. But the point that I'm trying to make on this slide is not just that the design space is very large, but also that the intersection of proposals is very small, both because proposals generally choose different types of control, but also because these proposals don't generally compose. From a mechanistic standpoint, it's very difficult to imagine implementing more than one of these proposals, which is another way of saying that if we were going to deploy this, if we had enough momentum to actually deploy one of these, we would get to choose a box, and we could get all of the controls represented by a box, but to the exclusion of the controls represented by all of the other boxes. And so given this, which doesn't seem entirely satisfactory, because, of course, our sympathies are all over the place. So in looking at this design space, it's worth asking ourselves, what are our options? And one option is just to say, well, look, the internet has been transformative. It's been awesome. Don't mess with it. We'll just embrace the status quo and do nothing. There are those of us who do not view this answer as entirely satisfactory, both because these proposals have had excellent motivations. They're providing key properties for key stakeholders, but also because now seems to be a moment where if anything's ever going to happen, it's probably going to be right now. There's enough momentum on internet changes, and even if it only happens in a test bed at first, there's still enough momentum. So looking at taking this design space of sort of mutually exclusive proposals and saying, well, we're going to, they don't agree, so we're not going to even look at one of them, seems to us unsatisfactory. Another thing we could do is say, well, yeah, they don't totally agree, but we'll look hard at the picture, and we'll pick one of these proposals. We'll pick some of the controls that are represented in that proposal, and we'll go and we'll deploy that. This doesn't seem like a great idea either. Given the lack of consensus about which stakeholders and concerns are most important, this would actually be a gamble. Unfortunately, it's worse than that because it would not just be a gamble, it would be a high-stakes gamble since we're not going to get that many chances to make this change. So ideally, anything we come up with should last for another 30 or 35 years. But it's even worse than that because it's not just a gamble or a high-stakes gamble. It's a losing high-stakes gamble because as a community, we researchers, the founding internet generation, whomever, we've been terrible about predicting the future of the internet. And so neither of these two options listed in blue there really seems particularly ideal to us, where us here refers to my co-authors and me. So there's a third option, at least that we could imagine, and I'm sorry for the microphones being noisy. There's a third option, which is to ask, well, look, there's all these great proposals out there. There's all these great controls. There's all these key stakeholders. Is it possible? Is there some sort of principled union of all of these? And the advantage to looking for a union is that, in some sense, this is the most future-proof strategy we could think of. This is the strategy that avoids making guesses in the present about things that are unknowable in the future. And also, this strategy, if it's possible, avoids picking winners and losers. And by winners and losers, I don't just mean winning and losing proposals, but also winning and losing stakeholders, right? We can expect that if there are some stakeholders whose interests are not upheld by some class of proposals, then we could expect them to fight the adoption of any future architecture instead of endorsing it. And so purely for pragmatic reasons, it would be awesome if there were no winning and losing stakeholders. The approach of a principled union seems to be the only one, at least to us, that has the potential to empower all stakeholders. And so that's what we're going to strive for. I've circled this I've put a quadrilateral around it in red to indicate that this is going to be our primary concern in this talk. And I guess I mean my primary concern, since I don't know if it's, I know it's not Alex's primary concern. So this is what we're going to try to do. If the challenge, of course, is it possible to identify a principled union? And then once we've identified one, is it possible to uphold that union with one or a small number of mechanisms, since you don't get to deploy like 35 different things inside a forwarder that needs to run at 100 gigabits a second? Yeah, Alex.
So I'm going to channel Dave Clark for a second.
Please.
This would fail his test of an architecture, right? So Dave Clark loves to run around saying that an architecture is deciding what should be left out rather than what's in. And basically saying, anything you can think of, we can do.
Well, but Dave, the great thing about somebody like Dave Clark is I can then point to something else he said and say that, this would be upheld. And, Dave Clark just becomes our Bible or the law. Dave Clark says you should modularize around tussle spaces. And, Dave Clark has a lot of great insights. But as far as I can figure out the tussle space of which entities should actually have control, designing the playing field, not the outcome, which is another thing he said, seems to favor an approach like this. So, to the extent that David Clark is like a book of Zen koans, I don't think it's fair to say, this fails his test. Certainly he's got a lot of insight, but, half of the things he said could be used to argue in favor of this, and the other half could be used to argue against it. So I don't know what the...
Fair enough. So let me take it out of
Okay.
This seems like it's deferring the problem.
Most definitely. You don't get to build... That's like saying that IP was deferring the problem of which particular... protocols that ran on top of TCP would be most important because they never saw the web coming. I mean, absolutely. You're trying to design an architecture that can accommodate a range of concerns and you don't want to choose in the present. So yeah, it's absolutely deferring the problem. That's why I describe it as the most future-proof strategy possible.
I guess I'm saying we do nothing, and that's also future-proof. Someone can show up anytime and do the right thing because we haven't done the wrong thing.
Well, there's a liveness and a safety. I mean, this is the thing. I've been at UT for long enough that I start thinking about things the way my colleagues, the very smart Lorenzo Avisi and the very smart Mike Dahlin think about things as liveness and safety. So I view the first one as being purely safe, but has no liveness property. And this has ideally a safety and a liveness property. And both are needed for correctness. A solution must, you don't get to say a solution is correct if it's not live. Okay, that's neither here nor there. It's the 2 hours of sleep talking. Okay. So this principled union is our concern, and the question is, well, what would a unified set of policies look like? And one observation is that many of these prior proposals, at least at the interdomain routing level, we'll talk about other concerns as well, at the interdomain routing level, they all correspond to some entity along the path of a communication exercising control over some aspect of the path of the communication, whether it's the sender, or they're controlling whether it's the sender or a subsequence or whatever. And if we generalize slightly, it looks like if we were to exclude the set of controls represented by this, that every entity along the path of the communication should be able to formulate policies based on the end-to-end path, that if we were to rule some of the controls represented by that statement out, that there would be important concerns that wouldn't be accounted for. And so our policy principle is this, plus some other things I'm going to list, but that each participant have the ability to formulate policies not just on some component of the end-to-end path, but on the whole thing. Entities also have other network policy considerations. They care a lot, when a packet comes in, they care a lot about a provider, for example, has to make a decision about the internal packet, and by internal I mean intra-domain packet disposition. I'm an ISP, I get a packet, I have to decide, am I going to send this over an expensive long-haul link, am I going to try and eject it from my network, etc. Today, providers make those decisions, they can't make it on the basis of anything other than the information that happens to be in the packet at the moment the packet arrives at the provider, right? The packet has no other information to go on. But it's possible to imagine other considerations that a provider would have that would cause it to dispose of a packet differently. For example, whether a sender has paid their bill, what time of day it is, et cetera. And I'll have more to say about these considerations later in the talk. But my point here is that these three things, an entity's being able to formulate policies on the basis of the full end-to-end path, on the basis of the internal disposition that would be associated with the given flow, and on the basis of arbitrary other information. I just want to clarify that by arbitrary here I mean unconstrained. That is, I mean arbitrary in the technical sense rather than in the non-technical sense of tyrannical or something. So on the basis of that third thing, I argue that this is more general than and subsumes many, something like 40, 50, 60 prior proposals and defenses at the network layer. And of course, once I've said it, I guess it sounds pretty obvious. It looks pretty obvious in hindsight to us, so I won't belabor the point. But if we could uphold this policy principle consisting of what's listed in blue, and I've depicted it graphically there, we would, I would argue, have a unified policy framework. Okay, so that was the first part of the talk, what policy considerations should be supported. Then there's this question, how the heck are we going to uphold this? Is it even possible to build a supporting mechanism? This is what I'll talk about in the second part of the talk. There are a number of technical challenges that I'll turn to in a moment. It turns out that they're challenging enough that I'm going to set a low bar for myself. I hope to sail over that bar, maybe not. I'm going to try to convince you only that it's feasible. I'm not going to try to convince you that our mechanism is awesome, even though I think it's pretty cool. I'm just going to try to convince you it's feasible. We have actually implemented it in hardware. The system or the mechanism is called ICING, so I'll be using that term as the talk goes on, ICING. And then the third part of the talk, which is related to the mechanism piece, is what are the uses of this? What can we use ICING for? Yes? Yeah. However, I mean, this is only, this is basically a visual metaphor. But essentially, every entity along the path, they may choose to delegate or abdicate their control, but every entity along the path of the communication, in theory, has the ability to formulate policies based on the end-to-end path. So it's going to be a square, right? It'll be n by n, and n is the path size. So it depends on the size of the path. Okay? But, I mean, this isn't meant to be, there's not a formal translation. I mean, I had the design space depicted in abstract terms, and you shouldn't take that too literally. You should take literally that every entity along the path should be able to formulate policies based on the end-to-end path. Okay. Yeah. Definitely. That's something I'm mainly going to punt, but we definitely do. That is definitely something that we have to think about. Totally. Because I want it to go this way, you want it to go a different way, what happens? So I'll talk about that later. Ask me if I haven't. Okay, so I'm going to move on to the second part of the talk, whether it's possible to build a supporting mechanism. Oops. So what are the technical challenges? Well, first of all, if we need for the control plane to be able to specify arbitrary, and again, I don't mean arbitrary in the sense of tyrannical, I mean arbitrary in the sense of unconstrained. If we want the control plane to be able to specify arbitrary policies, we're going to have to think hard about what the interface is from the control plane to the data plane. The control plane is going to be able to express policy, but how is it actually going to express policy to the data plane is challenge number one. Challenge number two is, once the control plane's expressed policy to the data plane, how do we actually enforce policy? And it turns out that actually enforcing policy, I mean, I'll describe it, but it requires new packet authentication techniques. Neither the status quo nor other proposals are actually can enforce policy the way we mean enforcement. And there are other challenges as well that I wasn't planning to focus on, but may come up in the process of my explaining this. Entities should be able to delegate their control to other entities or abdicate their control. There's a bootstrapping question, namely how a communication gets bootstrapped, that I won't focus on too much. I hope the answer will become clear as I speak, but I'm not going to address it explicitly. Okay, so, all right, so the technical challenges, the top two are the ones I'm going to focus on here, and I'm going to move on to the first of them. What should the interface between the control and the data plane be? Well, one observation is that today, the control plane and the data plane in a router, this is a router, this square represents the control plane in a router. One observation is that those are generally conflated. They're implemented in the same box, which of course hinders the flexibility of the control plane. But if we want entities to be able to demand arbitrary information before expressing their policy decisions, then policy decisions actually need to happen prior to packet flow. And we'll see later in the talk what the advantages of this are. But if policy decisions happen prior to packet flow, there's no reason at all that they should be happening in routers. Routers are expensive. They're hard to modify. They're great for packet forwarding and bad for making policy decisions. So what we want to do is once the decisions have to be made prior to packet flow, we might as well move them to general-purpose commodity servers, which are evolvable. I think a point that Amin and those of you working with Amin could certainly relate to. And I'm depicting that here by taking that square and moving it off of the router and into what a bigger square, general-purpose servers. And so in thinking about the interface, and I guess I delegate. I keep saying delegate or abdicate. So certainly I'm going to depict the general form of the design in which servers can control, or servers have the ability to exercise control, but they certainly can delegate that control. So now in thinking about what the interface to the data plane is going to be, a sender, for example, would submit to one of these servers. It would have to submit any information that the server needs, as well as the end-to-end path. The end-to-end path needs to be an input to the decision because we said that entities should be able to formulate policies based on the end-to-end path, which means the end-to-end path needs to be manifest at the beginning of the communication. Now, some stuff, I just wrote stuff here, is going to get returned from the general-purpose servers to the sender. We'll talk in a moment about what that stuff should be or what it has to be. And then the sender is going to take that stuff and use it to create other stuff along with the data that it actually wants to send. And so the question about what the control data plane interface should be corresponds to what should be in the stuff and what should be in the other stuff.
Are you going to talk at all about how we got the path info? Or are you going to
path, comma, info. These are two components. How did we get the information, or how did we get the path? We got the path probably through a routing protocol, but we could have done it through a name lookup. I mean, one cool thing about this is that because routing and path selection happens off of the data plane, you can push it, you could conflate it with the name lookup process.
maybe I don't care what path it is, and so now the person who gave me the answer is expressing policy as part of the path.
Okay, fine. I mean, that happens today when you go to a content distribution network. They're expressing policy based on, at a course level, they're exercising a form of receiver-driven route control. You don't.
So there's a whole bunch of other policy that happened before this, which somehow I came up with that. So your point is that the mere routing, the routing, absolutely. The whole point of this is that we can run any routing protocol on top of this. Yeah, absolutely. That's definitely part of policy as well. But your model is something else takes the path, and now you're just going to decide whether or not you're going to use it.
For the purposes of this talk, yes, although we have also done work in which the path, we compute the path as well and push the path to the edges. But for the purposes of this talk, my concern is mainly going to be the control data plane interface and enforcement in the data plane. I hadn't planned to talk too much about how the control plane computes the path. But the short answer is there's a routing protocol. This shouldn't make you nervous because today you can do name lookup, so there's no reason you couldn't do a route lookup. Okay, so I had actually planned to talk about the control data plane interface at the whiteboard for reasons of exposition, because I think there's some stuff that I'm going to want to leave up as I describe enforcement. So I hope you'll bear with me as I draw on the whiteboard. Okay, so the control data plane interface here. I'll just write I face for interface. Can the folks in the back, am I writing large enough? I mean, can you see? Okay. All right, so we said that there's a sender. We said that there's a consent server. Oh, we didn't say consent server. I'm going to call it a consent. These general purpose servers I'm going to call consent servers. Consent server. The path and some info gets submitted. Now what gets returned is going to be, we're going to discuss the exact form of this, but I'm calling it a proof of consent. Proof of consent, or POC. POC, and then here's the router. This is the data plane. What's going to be in the packet, I'll specify part of, but not all of. I'll move on to specifying all of it as we address the second challenge. And I've done a terrible job drawing the packet, and I'm sorry. I feel like I'm on one of those cooking shows. All right. They're narrating every time they drop the wrong thing into the wrong ingredients. All right. So basically what's going to go in packets are going to be information per hop, that is per hop in the path. We could call that hop info. A hop info consists of a realm ID. A realm is just our word for example, a domain. It's a unit of trust and control. We're going to have this thing that we call a vnode, which you can think about as bottom bits on the realm ID. They help create virtual realms within a single realm. So if a realm ID, if there's a different vnode associated with the realm ID, that's like different logical networks, even though it may actually be running on the same physical hardware. And then there's this thing that I'm going to call a verifier. We're not going to describe the precise form of a verifier yet, but I'll draw in two hop infos, and I'll draw a triple line here for different hop info. Oh, man. Okay, realm ID, vnode, verifier, etc. And so the interface to the data plane is just this. All that the interface is, which I don't know, we certainly think it's pretty cool, are just realm IDs, vnodes, and POCs. That is it. If the sender can assemble the right policy can be expressed with these proofs of consent. This is a token indicating that the consent server approves of any information the sender sent to it, which includes the path at the level of realm ID vnode pairs, all the way a sequence of realm ID vnode pairs. This proof of consent is a token to the sender indicating the consent server, which is associated with a particular realm. There might be another data plane forwarder here, data plane forwarder, data plane forwarder, another consent server here, and so forth. That the interface is just realm IDs, vnodes, and POCs, and that what we'll see is that the data plane works with many control planes. Just these objects, realm IDs, vnodes, POCs, are enough to allow any control plane to express its policy to the data plane. Yeah. Yeah, please do. No, I'm sorry. So you're doing really well. There's actually a whole bunch of hop IDs, as many as were being n in that n by n matrix. So each one, you can think about this as like a form of loose source routing, where there's one of these triples for each entity along the path. Okay? The other thing is that the realm ID vnode is the generalization of the ID of a hop, and the verifier is going to get transformed as the packet travels. So it's not actually part of the ID. It's cryptographic information that's going to be transformed. It's going to help uphold our second goal. Yeah, and then.
So it is correct to understand that the entire path is negotiated in advance for every packet?
For every flow, not every packet. And in fact, it may not even be every flow, because if you keep gaining access to the same destination in exactly the same way that your DNS server has the information cached.
But even so, right, so it's a pretty heavy overhead, because right now there are very few constraints in Bevy. Now you've got all the rules, not everyone knows all the rules at the same time, and yet when you establish a path and negotiate, essentially all the trade-offs and negotiations between the stakeholders happen at runtime.
They don't necessarily happen at runtime because, so there's two things. Number one, the overhead is not as bad as you might think. In fact, it may not be bad at all, because we could conflate this entire process with name lookup, which you have to do anyway. You have to make a DNS query usually. Most of us don't type in IP addresses when we gain access to websites. I mean, I'm sure that some subset of you does, but most of you probably don't. The other thing is that the point about delegation and abdication are key. If an entity, I mean, one way that we've articulated this is to say that the architecture doesn't charge for unused generality. So if there's some entity that doesn't actually want to exercise control, it delegates its control to the edges, and there's no negotiation on the part of that entity. If that entity needs to exercise control or wants to, then in the general form, we have no option but to do this to uphold their policy considerations. Does that answer your question? Okay, yeah. Please. Most definitely. So AS or domain would be a realm, yeah. Who's you?
So if because right now
So-
you have a path where you have to, there are many hops, so all of this have to be specified.
They'd have to be specified, but they may be. I'll show how we can implement BGP on top of this thing for no extra overhead versus what a communication costs today, other than some cryptographic trick or some cryptographic work. So if an entity doesn't care to exercise more than the control that it has under BGP, then then we don't add any overhead over what BGP adds. Does that answer your question? But the whole path is manifest in the packet. There's a space cost to ICING, and I'll talk about that space cost in detail. But there isn't necessarily a control plane cost beyond what's necessary to uphold people's policies anyway. Okay, and that seems unavoidable to us. Other questions? Okay, so this is the control data plane interface. I had said before that there's another challenge, which is actually enforcing policy. So, okay, great. The consent server said, yeah, great, I approve of this path. The sender's taking all of these proofs of consent. Remember, this is the stuff here. Remember, I'll draw it in blue. Maybe it'll trigger memory. So this was stuff, and then there was stuff in the packet called other stuff. Okay? And that other stuff was somehow going to have to be enough for the data plane to enforce policy. Now, the reason this is actually a hard technical problem is that we want to do this stuff at high speed and in a federated environment. So specifically, we need for the data plane to be able to check, given a packet, that the path in the packet, remember all the realm IDs are manifest in the packet, that the path was actually authorized by remember, the general purpose server and the forwarder are physically separate. So given a packet, the forwarder needs to be able to check that the general purpose server signed off on the path. You can imagine ways of doing that fairly efficiently, but the actual technical problem is far harder because we don't just need to check, given a claimed path in the packet, that path was authorized. We also need to check something much harder, namely that the authorized path was actually followed. And if you think about the typical techniques you might imagine for this, like a log and packets with digital signatures and so forth, the natural solutions are totally ruled out by the speed and scale at which we want to do this. So backbone speeds preclude things like RSA public signatures or a natural list of digital signatures in a packet. The scale of the internet, the trust relationships are such, the internet is mostly federated. The trust relationships are such that we don't want to have to assume any sort of public key infrastructure. We can't assume that entities have pairwise configured shared keys, right? You could imagine that, well, if every entity if we had configured every entity to share some secret, we could make this work somehow. No, we cannot assume that every pair of entities has pre-configured a shared secret. They will need shared secrets, but they're not pre-configured. That's a hint of coming attractions. The other thing I want to observe is, lest you think that this problem is totally easy, the status quo is nowhere close to this. BGP's routes are totally, the routes that BGP computes are not only, they're just, they're a BGP advertisement, I like to say, is just an advertisement. Nothing actually constrains the data path. So Alex and I are exchanging BGP messages. We're two autonomous systems. I know that he really wants me, traffic, or I know that he's advertised that he's going to send traffic along a particular downstream AS path. I send the packet to Alex. There's no guarantee that the packet's going to take that downstream AS path. This is one problem with source routing, for example, that there's no enforcement. So I just want to observe the status quo is nowhere close to the two bullets above. So the question is, what do we actually do? What we do is we go to the whiteboard. All right. So the second challenge is, I'm sorry for the mic. Is there any way to should I just turn the microphone off? With the microphone or without?
Leave the microphone on because we need it for the recording.
All right. So how can the data plane enforce policy at high speed? And there's two things that have to happen. We need to check that the path is authorized. Oops. We need to check that the path was followed at every forwarder. Every forwarder needs to do that check. One of these is much harder than the other. I'll discuss them in turn. So one thing you could imagine doing, right, is you could take this proof of consent, this POC. So one option is, and this is actually what we do, so I won't put a question mark here, but you could have the POC for a realm I actually equal a MAC of a shared secret. So let's assume this is the shared secret for this V node. I'll call this V1. I'll call this V node V2, SV2. This is a shared secret. You could imagine having the POC, which we do, be a MAC of a shared secret and the path and some expiry time so the permissions expire along with the expiry. Right? So what this allows right now, if I take the POCs, if I'm designing this, and I have the verifiers actually be these proofs of consent, what I could do, sorry. I'm sorry about the loudness. All right.
Put that on, then I'll turn it on, so we don't get all the rumbling noise.
Perfect. Okay. So you could imagine, I will speak quietly. You could imagine that if this verifier were the proof of consent itself, that this would actually uphold number one, that the path was authorized. Right? If I just put the POC into the verifier field, a data plane forwarder gets a packet, it checks its own hop info, right? Because there's a sequence of these. It checks its own hop info. It compares the contents of the verifier field, which are a path, macked with a secret. It knows the secret, and it could check that the path was authorized. What it could not do is check that the path was actually followed. So the next part of the problem is to check that the path was actually followed. This is a little bit harder, and I will try and give you a sense of the approach. Are there questions before I do this? All right, so I'm going to call this provenance. Did the packet take the path it was supposed to? And provenance requires pairwise knowledge, or it seems to require pairwise shared keys. There's actually, after we did this work, we saw this this theory paper in which people proved a lower bound. Like if you ever wanted to do something like provenance in a network, every entity had to share keys. So it was just impossible to get provenance, because how the heck are you going to get pairwise shared keys? You can't configure the network to have that. And we were totally stoked because we did not violate that lower bound, but we found a way around it, not realizing that there was this lower bound. So there is this lower bound that if you want to do provenance in a network, you do need pairwise knowledge. And the question is, how are we going to get that pairwise knowledge? We can use a trick. And so the trick is that the realm IDs are short public keys. And if you imagine that the public key is something like, so realm ID R, or let's say R sub I, equals G to the X sub I, where X sub I is a private key, X sub I private, G is some globally agreed upon generator. It doesn't matter. If you do that, then Ri and Rj can each compute K sub I comma J just by Diffie-Hellman, which equals G to the Xi, or I'll draw it like this, Xj. The idea is, if I'm some realm and I know my own private key and I know your public key, I can compute a secret that you will also be able to compute from knowing my public key and your private key. This is just Diffie-Hellman key exchange proposed many, many, many years ago. But the advantage to this is that because the way we get around this lower bound is that because the packet is traveling with a set of public keys anyway, and because each entity knows its own private key, it's able to infer the pairwise shared secret that it has with every other realm. And so we're implicitly able to derive quadratic state. We never need to materialize the quadratic state, of course, but we're implicitly able to derive a quadratic number of parameters. And once we have those quadratic parameters where every entity implicitly shares a key, provenance isn't too hard. And so the actual approach from a mechanistic standpoint looks like this. The actual, I'm going to can I erase? I'll erase this. So the actual verifier, v sub I, that the sender is going to put in the packets, it's going to start by setting vi equal to the POC itself, XORed with the MAC. The key, this is starting from the sender. The sender is going to set this up. Maybe it's some entity acting on behalf of the sender in the sender's local network. It doesn't matter for the purposes of this discussion. It's going to MAC it for each I along the path. The sender is going to create a MAC with its own shared key, or the key that the sender shares with that entity I. And what it's going to MAC is going to be some function of the packet. And anybody can compute the invariant fields in the packet. I mean, the hop ID changes as the packet travels. The hop ID should not be an input to this hash, of course. OK, so that's v sub I. Or we can imagine that this is v sub 1, v sub 2. Actually, let's make this POC1, POC2, XORed with MAC of k sub 0, 2. Hash a packet. OK. So what happens as this thing travels? Well, what happens as it travels is now a realm needs to do two things. When a packet shows up at a realm, it needs to check that a bunch of MACs are applied correctly, because essentially what's going to happen is that as the packet, let's say that, let's say that this is realm, can you see in the back? Okay, let's say that this is realm J. What realm J is going to check is whether the verifier that corresponds to itself, right? Each realm has its own verifier. It's going to check that the verifier that corresponds to itself, v sub j, equals the POC of j, which, remember, was issued by its own consent server. And so and therefore, the forwarder can derive it, whether that's going to equal an XOR of, let's say, a giant XOR from I equals 0 up through j minus 1 of this MAC thing. K sub I j. Do people see what's going on? That we're creating a layered MAC, so that by the time the packet shows up at a realm, the packet should have been MAC'd by every single entity before the realm on the path. People roughly cool with that? Roughly cool with that? OK, so once the packet shows up like that, remember that the forwarder has all of the information to compute that verifier itself. So all the forwarder has to do is compute that exact verifier and see whether it's equal to the same value that's in the packet. If it is, the packet did not deviate from its path. It may have taken a detour, but every entity that was supposed to have handled the packet had to have done so. Yeah.
Maybe you're going to get to this in a second,
Yeah.
but it seems like if I care to screw with you, now, normally I can forward the packet or not.
Uh-huh.
But now I can forward the packet and alter some arbitrary verifier downstream such that somebody else is going to drop it.
OK.
And you can't figure out that I did it. Because you can only verify backwards, right? I can't go forward because the XOR hasn't built up. So why can't realm 2 XOR junk with the verifier in realm 5? So by the time it gets to realm 5, it's going to fail verification, and 5 is going to be forced to drop the packet.
But 5 is going to know that 2 screwed up.
Why?
Oh, sorry. 5 won't know that 2 screwed up. The packet will just look invalid. That's fine.
Yes.
But
a 2's been screwing with. Normally, 2 drops the packet, and it's very clear where the problem was.
Not always. I mean, but sometimes ISPs point fingers at each other. I mean, there's a whole literature in identifying today where problems happen on the internet. I mean, I assume that if it were so easy to figure out exactly where the problem was, then...
Well, so fair. Packet
I mean,
arrives at realm
so,
3.
Alex, I could...
Realm 2 is not exonerated, right? Just because the packet got to realm 3, realm 2 could still defeat the
Oh,
forwarding of the packet.
but that's always true. I mean, you could have realm 2 change bits in a checksum even today, right? Realm 1 could log, checksums or hashes of packets if you don't want to break anonymity. But what you could have happen is that as the packet's traveling, some entity messes with protocol bits that break the TCP checksum or something, and it's very difficult to figure out who did that. What you might be able to do, given sampling and so forth, is have 2 entities point fingers at each other, but there's a result, and it actually makes intuitive sense, that if a packet's traveling along and there's some problem, you can only ever localize the problem to a link. So the best you can do is have the faulty entities point fingers at each other. That's the best you can do today, and it's not trivial. In our framework, you're absolutely right. an entity can totally mess with the packet at the network level packet. I mean, this is obviously the network level header, but it's not clear to me that messing with the network level header is any different as an attack goes from messing with the application level header anyway. Just, it's just not clear. I mean, it might be, but so you're right. This may be a limitation, but it's not obvious to me that there are other limitations. But it's not obvious to me that this is like a major one. Other questions? So at this point, an entity, I mean, I've sort of run out of board space, which is a bummer. It's my own fault. When an entity gets a packet here, it not only checks, it not only recomputes the verifier, but it also has to do something else. The something else that it does is that it then has to take every verifier after it in sequence and apply its own key to it. So what I can represent this graphically like this. If this is the hop info in question and this is the verifier, and I hope there aren't people who are red-green colorblind in the audience because I'm going to use red and green, which I'm sorry about. So if there's like the green realm here and the red realm here, and then the packet shows up at the blue realm, it better be true that the verifier, sort of from a picture perspective, looks like it's been macked by the green, then the red, and then the blue. Okay? And a verifier can check this. I'm just depicting graphically the process of continually XORing things. Okay, but now I'm really out of color. How am I going to solve this problem? All right, so let's imagine that there's a black realm down here. Now the entity has to take this verifier, which also will have been green and red and blue. Oh, I'm sorry, I've messed. Let's say this is the one. And let's put blue here. So what will happen is this entity needs to prove provenance to the downstream entities, and so it will wrap the rest of the MACs, or the rest of the verifiers, in its own key. And so essentially, every time a packet travels through a realm, that realm has to compute a number of operations proportional to the number of entities in the path. That is, it has to check that every entity before it saw the packet, and then it has to prove to every entity after it that it saw the packet. Are we roughly clear on that? I mean, even if the precise details aren't clear, I'm hoping that picture gets across. So to just state the data plane, I'm now moving from the whiteboard back to the safer ground of PowerPoint. In a nutshell, I've depicted what ICING's data plane does. It carries the path. A given realm verifies provenance for all prior realms on the path using these shared keys, k sub j, kj sub I. A realm I proves provenance to all of the realms after it using ki sub j. I said before that it was unacceptable to have pairwise configured keys, and we get around that because a given realm generates the shared key from the other realm's name. So there is no pairwise configuration. There is no quadratic state. This resists a variety of attacks that you could concoct. And so the remaining question, since I said before that the number of cryptographic operations as a packet travels is proportional to the size of the path, is this actual, one of you asked about space before, is this actually feasible, right? I mean, we're adding space to the packet header. We're adding computation as the packet travels. Is this thing actually, can this fly? And I claim it can fly. It's a little bit more expensive than IP, but let's look at the space overhead. So because we're using elliptic curve cryptography and short public keys, our public keys, the realm IDs are 20 bytes. This thing's 20 bytes, 20 bytes. The vnode that I talked about before is 4 bytes. So that's where we get 24 bytes up here. The verifiers, these verifiers are 16 bytes per realm. And then there's another 2 bytes for the expiry, for the timestamp. So if you add 24 and 18, you get 42 bytes. 42 bytes per realm seems huge, except for one thing. The naive solution would cost over 128 bytes per realm and be intolerable from a computation standpoint. The other thing is we're saved by the fact that most packets, even though 42 bytes per realm is a lot, guess what? Most packets are much larger. And so even if we add 250 bytes, that's only about 20% more space. Now, certainly, you might say 20% is a ton. I would say that, we're trying to look ahead, look to the future. Today's hardware costs, what seems expensive today often becomes commodity tomorrow. So I'm not too worried about 20% more space. You might wonder, well, okay, you're doing all this computation. What do you have to pay in logic, in transistors, and so forth? And So we implemented this on the net FPGA platform. And by we, I mean Jad Naous of Stanford implemented ICING. Everything I told you about runs in hardware on that net FPGA chip. We're able to do an apples-to-apples comparison of what ICING costs compared to IP because conveniently there was an IP router that also ran on the net FPGA and it implemented IP, and our implementation implements ICING, so we can look at what the relative costs are. Well, the answer is we cost a little bit more than IP, and for that little bit more cost in gates, we're running a little bit slower than IP. So if you normalize everything out, a natural measure here is gates, the number of gates you're paying per gigabits per second, right? I mean, if I'm running at the same speed, if I'm paying the same logic cost as IP and I'm running at half of IP, we can't call that the same hardware cost. So by scaling by the speed that this thing's able to drive a wire, we get that in gate and logic, relative to IP, ICING's about twice as expensive. You might say, well, twice is a lot, and that's true, but remember that what does Moore's law say? It says that every 18 months, the number of transistors you can put on a chip doubles. So yeah, it means ICING will be a little bit behind the technology curve, but it won't be ridiculous if you believe Moore's law, which does seem to continue to apply to routers and so forth. So in terms of the, I mentioned before that there is significant overhead from ICING. I've drawn it in a square there, 20% more space in the header, twice as much logic area. And at this point, I guess I should take a deep breath before moving on to quickly what the uses of ICING are. Just to quickly review how we got here, we started by observing there's all these different policy considerations. How can we create a coherent union? Our answer was the policy principle depicted graphically here. Then we said, well, this policy principle, how the heck are we going to uphold this? Is there even one supporting mechanism? I presented the data plane as an existence proof that there is a supporting mechanism. And now I'd just like to discuss a little bit the uses of the mechanism. Yeah?
In the last slide,
yes.
you overview the latency of it. Considering the fact that you have to target computations, the latency of the packet might take a bit hit.
There was one thing I didn't hear that you said. The latency, and then you said considering that, and I didn't hear what came after the that. That's completely captured here. If we're running at line rate, the extra latency to pipe the bits through the pipeline basically, so you're absolutely right. There is an extremely slight latency cost from the fact that bits have to go through a larger pipeline on the chip. But what really matters if we're running at line rate, as you know from basic networking, if you have a link here, it's true that there's some latency that you pay as stuff travels, but really the main cost is going to be end-to-end latency, and also you care about bandwidth. I've depicted the bandwidth here, and the end-to-end latency is almost entirely governed by the speed of light. So the fact that as a packet travels, it has to go through a slightly longer pipeline on the card is mostly irrelevant. But it's a good question. It just turns out not to be a big deal. Human beings can't detect an extra, few nanoseconds or whatever on the card. So you're right. There is wire delay, but who cares? Yeah. I think so. Our intuition isn't great here because most people think that cryptography can't be done at line rate and stuff like that. And I actually think that one of the contributions of our work is showing that you can do something non-trivial at line rate with not a lot of cost. So I just want to first set the fence that I think our intuition, all of ours, is probably not the best guide. But having said that, let me just observe that the latency you're talking about is latency on the chip versus the latency in a local area network. The latency that you're spending by increasing the pipeline, especially in something like NetFPGA, which runs at a pathetically slow clock rate, yeah, you're adding a little bit, but not compared to getting the bits from one end of your Ethernet or through the switch or whatever. So again, as a matter of scale, it just turns out not to be a big deal. Okay, and whatever latency we're going to realize, which is already negligible, is going to be even more negligible if this were on a custom ASIC. This NetFPGA thing is quite slow, and still things are fine. Okay, so in terms of the uses of ICING, I mean, I said before that ICING could be, its data plane could uphold a variety of control planes, and I promised you that I would show you how to run BGP on this thing, so I'm going to do that first. We'll see what else there's time for. So to run BGP on top of ICING, I'm depicting the forwarders here as data plane, data plane, data plane. You could just imagine that they run the same BGP messages that they do today, only the messages they exchange are, instead of having prefixes, they're flat identifiers. The AIP project by my advisor and some other folks showed that it's actually practical to have BGP messages be in terms of flat identifiers. So that's not really a problem. So then there's this question, well, what goes in the BGP, what goes in a BGP advertisement? Well, what goes in a BGP advertisement is what usually goes in the BGP advertisement, namely the downstream path, but also what we're going to do to make BGP run on this with no extra overhead, right? You guys were concerned about control plane overhead, is we're going to take all that cryptographic material and we're going to publish it to the it's mixing metaphors, but we're going to publish it to the world. We're going to take those secrets that are associated with different vnodes that are no longer depicted, but they were inputs to the POCs, and we're going to have everybody know all of those secrets. The consequence of which is that when the sender goes to a consent server and says, yeah, I want to reach this destination, that consent server could just be, for example, some local gateway or some local DNS server. That consent server has all of the material, all of the cryptographic material it needs to either return the secrets to the sender or, more conveniently, just to return the set of proofs of consent. And if you're wondering, well, the sender has to deal with all these proofs of consent, today when you do a DNS query, you got to parse the reply anyway. So essentially, if this picture existed, we would be able to run BGP on top of ICING, but there's a benefit, and the benefit is that we could actually enforce the policies. I said before that BGP is only advisory in the status quo. BGP wouldn't be advisory here because once a sender sends a packet, right, it's going to stay along its path. If somebody takes the packet and sends it somewhere else it's not supposed to go, that other entity will say, well, wait a minute, this isn't right. It will fail the provenance checks. The other sense in which we enforce BGP, which is not depicted and I don't really have time to describe, is, yeah, okay, fine, the sender's choosing a route that it claims is BGP compliant, but how do we actually make sure that that route abides by what BGP would have said? And that, it's a little bit subtler, but it has to do with the fact that these BGP advertisements are going to contain special vnodes, and then those vnodes will only connect to the right peers and downstream realms. And so through suitable choice of vnodes, through suitable configuration of vnodes, we can, as a bonus, we can run BGP on ICING, and then as a bonus, enforce it. Force BGP's policies. Now so that's a traditional kind of routing. Most people are comfortable with the routes that BGP computes, but I want to propose another kind of routing. I said before that receivers have interest in the paths that their packets take. We could allow for sync routing. People have proposed source routing on many occasions, but it's not just the source that cares about the paths that its packets take, as mentioned before. The receiver should maybe be able to control the path that packets take toward it. So you could imagine an approach where there's some public vnode where everybody can gain access to the public vnode, analogous to a name server, roughly. The sender issues a request to the consent server. What comes back from the consent server, roughly analogous to a name server, is not only a path to the destination, but also a subset of the permissions needed to reach the destination, at which point the sender could direct packets. Assuming the sender, for example, R1 had delegated to the sender the ability to mint POC1. But the point of this picture is that the path used to request permissions is not the same. Is not the same as the path that the sender uses toward the receiver, and the path that the sender uses toward the receiver is receiver specified. This would have at least two advantages. One is today people use content distribution networks and crude DNS tricks to minimize latency from when a client makes a request of a server. The server essentially outsources to the content distribution network and to DNS the job of doing a form of routing to minimize latency and cost. So we know that receivers care about paths, but also you could imagine that this destination is, this is some host and some, this is some spy or sensitive source or espionage resource or something, and the sender and the receiver in particular care a lot about which paths packets take en route to the receiver. So the receiver might say, listen, if you're going to contact me, it's like you say to your friend, listen, you can call me, but don't call me at my work number, right? So you can do the analog of that if the sender and receiver have sensitive information. A special case of sync routing, to return to the examples we had at the beginning of the talk, you could imagine that there's some enterprise, some organization that is handling traffic for its servers and its hosts. That enterprise wants to make sure, it wants to outsource traffic scrubbing or virus cleaning to some offsite scrubber. So we could certainly use sync routing for that purpose. This is just an application of sync routing. Should I go through access control, or should I wrap up? It's been precisely an hour. Okay, I'll wrap up. There's other uses of ICING as well, which I'm not going to talk about. There's some limitations, there were things in the talk I didn't talk about. There were aspects of ICING I didn't talk about. So if you had questions, quickly scan those, see if they're there, and ask me questions. We have future work, and so I'll just sum up. I mean, none of that stuff was that important. I know it's stressful to see all this stuff flying by, but it wasn't important. This is important. I don't know, maybe it's stressful. Maybe you guys are different. I always get stressed. Like, wow, what was the speaker going to say? I don't know, maybe you don't care what I was going to say. So I barely care. No. So basically, we started this by saying that there's a lot of great policies, right? But there was no consensus on the best ones. So could we come up with some unified policy framework that would account for all of these policies? We did so with that picture that's depicted there, which obviously stands in for a policy framework in which policies formulated on the basis of these various factors. Our candidate mechanism, we're not saying it's the ultimate solution. It's a candidate mechanism. It's a proof of existence that this policy principle can be upheld. It had to solve a number of technical problems, including the ones I talked about. I think one of the coolest things about it is that for the first time, we've been able to bind the data plane to the dictates of the control plane without, first at high speed, and second, without assuming any kind of centralized entity. You can imagine, for example, in the world of OpenFlow, those of you, or ethane, those of you who know that work from Stanford, you can imagine it's not too hard to keep the control plane bound to the data plane if they're all administered by the same entity, because the entity could just set up a circuit, for example. But we've been able to do this in a context in which there's no federation, in a context in which there's no centralization and at high speed. I tried to make the case that ICING is feasible. I'd say that today it's not totally implausible, and tomorrow, I hope, or in the future, it wouldn't be totally impractical. If you're sort of looking for what's going on here, what are these guys taking advantage of, what's going on from a technology standpoint, bandwidth and computation keep getting cheaper. You're able to do more and more on a card, for example. And so what we're doing is taking some of that extra resource and exchanging it. We're spending some of that resource in the form of overhead for properties that we don't have today, like, for example, a coherent policy and security. Whether you think those properties are worth the price is obviously a personal decision. I happen to think it's at least worth investigating, because the questions that we're able to answer now were not even questions we were able to ask before. So to the extent it's expensive, sure, it's expensive, but it allows us to ask new questions. So that's all I was going to say, and I'm happy to take other questions. Yeah. I
was curious about network failure.
Oh, dude, that's awesome. Okay. Okay, so I didn't talk about network failure. You're totally right. Limitation of this talk, not a limitation of ICING, I would argue. There are limitations of ICING. So for network failure, there's a few things you could imagine. One is that at the time that a route is computed, the part of the ICING I didn't talk about, you could imagine that the sender gets a few paths. We also have signals traveling backwards. So if there's a packet drop or a router notices that some link isn't working and a packet enters the link, or a packet's destined for that link, the router will send a message backwards, roughly analogous to ICMP. Okay, so if the sender had backup routes, we're good to go. The sender just uses the backup route, the backup paths, and the backup POCs. What if the sender didn't? Well, then the sender has to do the route computation, and then there's this question, is that actually expensive? Well, I don't know. Today, in the status quo, there's this myth that the internet sort of routes around failure. I mean, the internet does route around failures, but there was like this science fiction idea that here's the internet, here's a bunch of routes, there's a failure here, and boom, this router notices it and sends it somewhere else. That is not how the internet works, as many of you know, but probably not all of you. The way the internet actually works is BGP reruns and recomputes alternate routes. That process can sometimes take up to minutes. So it's not obvious to me that our route computation would take up to minutes. Yeah. Yeah, so I totally punted that, and we don't actually, at least what I've been trying to do here is think about what should the data plane, what should the interface to the control plane be, and this sort of gets into the David Clark-like point, the DDC-like point. about tussle space. I mean, one thing you could imagine is that connectivity is a powerful enough driver that we're just going to let the future figure it out. If there is a conflict, it's not the case that nobody's going to be able to communicate, because it's so important for people to communicate, and there's so much money at stake, and other things as well, that somehow, essentially, the warring factions would duke it out. But there is no mechanism that we have for resolving conflicts. Yeah. But here's okay, so if that happens, if my sender policy conflicts with the receiver policy and the sender knows that, the sender can find a route, right? Let's just assume there is a route that agrees with everybody's policies. ICING allows the senders and receivers to at least identify that route. Today, if the communication happens to violate any one of the entities, right? I mean, today you get absolutely no choice of paths. Maybe you buy service from 2 ISPs. Maybe you succeed in giving your ISP to give you 2 IP addresses. And maybe you succeed in having your ISP route those 2 IP addresses differently, which is very rare, right? But you get no say over paths today. So if the network, if your path would somehow, or that the network doesn't like the sender or doesn't like the receiver, you're out of luck today. Under ICING, it might be true that that path negotiation process has to keep running, but if there is some path that they're all cool with, which I argue there would be because connectivity is such a powerful driver, if there is some path they're all cool with, ICING will find it, or whatever control plane's in effect will find it, which is just like way better than the status quo. Yeah, that would be among the consent servers or name servers that are, for example, implementing routing. I mean, there's a whole set of control plane servers that I'm just sort of describing with the catch-all of consent servers. But I mean, actually, if I were going to describe this more precisely, I'd say there are path servers that actually run a routing protocol and from which a sender retrieves paths, and consent servers which issue these cryptographic tokens. And it would be the path servers that would actually run, and it would be up to the path servers to find a path for the sender. But you're right, ICING comes with no mechanism for resolving conflicts because it's not obvious how to resolve them, but at least we allow the computation to be prior to packet flow, so if there is a conflict, it'll be detected. I mean, one thing that people sort of, I do want to say this, none of you asked this, but I do want to say this because you may be thinking this. Some people are like, well, you're giving the ISPs all these power. You know, ISPs can say they don't like the path. Guess what? If a packet's traveling over an ISP today, it can drop the packet. ISPs can and do drop packets at will. At least with this, we allow the end host to find alternate routes. So this sort of, again, there's this thing that's sort of not intuitive where this seems to be empowering ISPs. I'd argue that any entity along the path of a communication is empowered, but at least this allows people to choose whom to empower, which I view as a fundamental sea change, or fundamental change. Right. So one thing I didn't talk about at all is that if your local ISP is messing with you, we have, because these vNodes basically function as MPLS labels, you could imagine the sender contracting for service elsewhere. The sender basically buying transit service from somebody it's not connected to. At that point, if your local ISP if your local ISP has a wire monopoly, yeah, you're screwed. But once, I mean, people have done this analysis. Xiaowei Yang has actually, Duke, yeah, that's what I thought. She's done this analysis, right, in the NERA proposal, where it turns out that if you give people selection over which core providers carry their traffic, something that doesn't exist today, then you can actually force competition among local providers. And the intuition is that the local providers that are going to start competing with each other for who provides access to those competing core providers. So this is actually a way that senders and core providers could actually negotiate. That's something that I didn't talk about, but is on was going to be on the slides. Does that make sense? I mean, it's a totally different way of doing things, so it's hard to talk. You know, it's kind of abstract, like, well, if we did this and we did that, you know, all these like subjunctives and contrary to fact hypotheticals, whatever. But it is true that there's no choice today, and this would provide choice. Yeah. You mean Jan Stojka? You mean, okay.
So that's using that as a concrete mechanism,
Okay.
you can actually answer maybe in some concrete way.
Okay.
This seems to blow away any hope of indirection, in the sense that you have to submit to, this is the entire path, come hell or high water, and I'm thinking about, I want to run it through some middle box that's then going to make some decision on the fly, maybe based on the content, maybe
So we can't right now, although I can propose a way to do it, it's just not efficient. We can't, with the mechanism described, and efficiently direct packets differently based on their payload at the network layer. But remember that Jan is treating IP as his link layer. You could treat ICING as your link layer. You could have the I3 nodes run two ICING communications between them.
Yeah, but then I lose all the benefits of this because then you're sort of only speaking over those links. I have to put the meta over this for the whole time.
I'm sorry, do you want the benefits of I3 or you want some way of incorporating I3 into this world?
I would like the benefits of ICING, but I'd like to be able to put a don't care in there.
Good. Excellent question. So Jan and I have actually, the future internet architecture stuff, we joined forces and thought hard about what a union of our proposals would look like. Short answer, these V nodes can map to one of his rules. He has this new proposal called RBF, rule-based forwarding, where packets contain rules, and those rules can allow packets to get handled differently based on their payload, which is currently a limitation of ICING, right? So, by the way, when I said that we captured all prior proposals, well, RBF, it was concurrent work. So we could have the V node map locally to one of his rules, and then, yeah, it's going to take some thinking about mechanism, but it is possible to transform the packet and do so in a verifiable way, and this is where the research comes in. But if I make my transformation explicit and I can put in the packet a log of what my changes were, then everything that I've described today would work. It just wouldn't be efficient.
But I still have to know it.
You still have to what?
I still have to know it at the beginning when I construct my list of verifiers. I have to pre-specify that this is going to be going through the transformer.
Yeah, you have to specify it's going through the transformer. We can't change the route in transit. That's right. That's right, except by directing it to a higher layer. But what do you mean, but then? I mean, it's again selective trust, right? If I send the thing up to a higher layer, and I trust this layer up here, trust in the technical sense of assume it's correct, even though there's probably no good reason to assume it's correct, right? So if I send to here, and this thing indirects, well, then I can trust this dude or this gal to send to indirect properly. I mean, this gets back to the argument that we made 5 years ago, that if you're actually changing things that are actually properly the province of the network layer, you should terminate the network layer tunnel or communication and handle the problems at another layer. So we could get I3 by just having, in the world of I3, de facto, if you're sending to an indirection point, you trust the indirector to do the right thing. We could do the same thing. And I disagree that we're losing all the benefits of ICING because I can still ensure that the packet travels along the path I want up to this entity. And then, yes, I have to trust that this entity does the right thing, but I had to trust that entity anyway, even under I3. You guys are like, who cares about internet architecture? All right. Alex does, even though he says he doesn't.
All right, with that.
Think different, man. Sorry that went on for a while.